Good afternoon, everyone. Can you guys hear me well? Great. Today we are going to continue learning about stereochemistry. So remember, during the class, any questions you might have, just please uh, send me. You can just raise your hand or just write it, type it on the chat. Okay. So uh, I want to start today by reviewing some ideas that we covered in the previous class, okay? So in the previous class, we were talking about classifying compounds when they have the same molecular formula and they have different connections in between the atoms or not, okay? So one classification that we actually did was to say if we have a few compounds having the same molecular formula, we will classify them as isomers, okay? Obviously, if they don't have the same molecular formula, they are not isomers, so they're just different compounds which are unrelated to one another. Isomers, of course, are also different compounds, but they have this relationship of having the same number of atoms, basically. Okay? Same for both. So isomers then are molecules with the same molecular formula, and then within isomers we have subdivisions. So the next question we asked in the previous class is, do these compounds have the same connectivity in between the atoms? And I gave you some examples of that. So when the compounds don't have the same connection in between the atoms, we classify them as constitutional isomers. Of course, constitutional isomers are compounds with different physical and chemical properties. However, we also went over cases in which there are compounds with the same molecular formula and the same connectivity in between the atoms, and we call them stereoisomers. The reason for that is because they basically differ in the arrangement of these atoms in space. So stereoisomers are compounds with the same molecular formula, exactly the same connectivity, and different arrangement of atoms in space. And we went over the consideration of this special aspect of molecular structure, which is called stereochemistry. Okay? And stereochemistry is a whole world in chemistry, and particularly in organic chemistry. We'll see more today about it and why it's so relevant. So we also saw in the previous class that stereoisomers, so compounds, once again, same molecular formula, same connection, different orientation space, could be classified, subdivided into two different groups, enantiomers and diastereomers. Okay, so diastereomers are stereoisomers which are not a mirror image of one another. So if you have two molecules with the same connection, same molecular formula, they are not a mirror image of one another, so we can classify them as diastereomers. On the other hand, if you have two compounds which are stereoisomers, but in addition to that, they are non-superposable mirror images of one another, we can classify them as enantiomers. And this is a big thing because, as we will see later today, and more so next semester, diastereomers have completely different physical and chemical properties, meaning that if you have a mix of diastereomers in a lab, they will have different, for example, melting points. solubility. Molecular structure differences in between them will be noticed in different methods that chemists use to determine molecular structure, like mass spectrometry, nuclear magnetic resonance, and techniques like that. However, enantiomers, which are the mirror, non-superposable mirror image of one another, they have exactly the same physical properties. So they have the same melting point, the same solubility, same polarity, same spectral features, which basically makes really hard to tell when you have in the lab a mix of enantiomers, and we will see later why is that so important and how we can determine that. Okay, so one of the things that we were working on in the previous class in regards to these basic definitions was to look at molecules in 3D, and that's one of the major skills that we have to actually develop in the class. So I'm going to show you here first a couple of examples, and again, we went over this. I'm going to give you, for example, something like this, okay? And one of the things that I said before is that when you see a couple of compounds, right, we define in class what is exactly the definition of non-superposable structures, okay? Here we have an example of two compounds, and I'm going to go over again the basic things that you need to know, the steps that you need to follow, okay? So first of all, as we discussed in the last class, when we use a line and angle notation, which is what most chemists use in textbooks and scientific papers, the agreement is that the flat lines are representing bonding that are actually located in the plane of the paper, in this case in the plane of the screen, okay? So every flat line is actually in the plane of the screen, and then we use this symbolism of wedge bonds and dash bonds to indicate now 3D structures of these molecules. For example, every single carbon here, as you already know at this point, and this is the one important thing, is that it's sp3 hybridized because there is no pi bonds whatsoever. sp3 hybridized carbons are carbons with a geometry that is tetrahedral structure. It's a tetrahedral structure. I'll see if I have a, and therefore it is really important to understand that actually the angle in between all these structures is basically 109.5 between the bonds, okay? So that's really important to keep in mind. Because, you know, if you really don't understand that, it's going to be very challenging to see the molecules in 3D, okay? So we need to really understand that every sp3 hybridized carbon is a tetrahedral structure, and what that means. I'll show you now a better picture of that. And then, as I said, okay, so somebody had a question, go ahead.
Professor, so the question is the 109.5 degrees, right? It's between all the bonds, even the ones out of the the screen, like the wedges and the dashed lines, or no, just the ones that are on the plane?
All the bonds, right? So I'm going to show you here a zooming of this carbon, for example, okay? How many bonds do we find in every carbon that is sp3 hybridized? What's the total number of bonds in every carbon? 4, right? Correct. So 4 bonds, and this could be the geometry of those 4 bonds, right? So we have angle here will be 109.5, angle here will be 109.5, angle here will be 109.5, angle here will be 109.5. Can you see that?
Like that?
Yes or no?
Yes.
So the way to draw this and I'll show you now a model so you will see it much better in 3D. But the way to to look at this is, so in this molecule here, the two CC bonds are on the plane of the screen. Okay, this carbon-oxygen bond is coming toward you. Okay, and this carbon-hydrogen bond is going away from you. All right, and that's 1.5. That's a tetrahedral structure. So we need to start looking at this in 3D. Okay. Of
Okay.
course, in every carbon here, you have two hydrogens. One will be coming toward you, one away from you. Here
Got
too.
it. So when we see these on paper, basically, we have to, in our mind, think of it as a 3D structure.
Exactly. That's what you gotta start doing from now on. Okay. If
Oh,
there is no group bonded to a carbon, since it's two hydrogens and two hydrogens is the same atom, people don't care which one is coming toward and which one is away because it's the same thing, right? But
oh,
once you have something different than hydrogen attached to a carbon, then it's very relevant to mention which one is coming toward you and which one is going away from you,
got it.
like in
Thank you,
this case.
Professor.
Okay?
Yeah, got it. Thank you, Professor.
No problem. So one of the things that I said that is important for you guys is to be able to determine relationships in between molecules, okay? And that's so important because uh, that's one of the skills that we need to have in orgochem and in any basic chemistry, advanced chemistry class, right? So, and we kind of practiced that in the previous class, okay? So I want to review that again because I know that it's challenging, and I hopefully today will be better understood, okay? So here we have three molecules, okay? And once again, if we want to look at the relationship between the three of them, so I'm going to say this is molecule A, this is molecule B, and this is molecule C. So molecules A, B, and C, if the question is, what's the relationship in between these three, we need to look carefully right between them. So remember, we need to superpose them and see if once they are superposed, they match 100% of it or if they don't. And before superposing, we need to make sure that we are doing the right flipping, okay? Because molecules can be flipped no matter what. And it's the same thing. As long as you don't break a bond, the molecule is the same. I'm going to show you now. Let's see if I can show you an application that I have here with a molecule in 3D, and hopefully that will make you understand better what I'm trying to say. Okay, can you guys see the molecule in 3D here? Good. So now I hope now you can see what I'm referring to, the 109.5. Okay, look at the molecules here. Okay, so that's exactly the molecule that I had on the other picture. So we have three hydrogens here, 109.5 degrees, three hydrogens. So one hydrogen and an OH group here, two hydrogens here on this carbon, two on this carbon, three. You see the 3D structure, okay? It's a 109.5. That's how this molecule looks in 3D, okay? Because every single carbon is hybridized. So I want to focus on this carbon. In this carbon, the hydroxyl group is going away from you, behind the screen, okay? That actually means that if you were to draw this molecule on paper, you will draw the line and angle notation, and then here you will draw a dash line, right, with a hydroxyl group. Now, I'm gonna flip the molecule 180 degrees. So this is a vertical flipping, and I said you can flip the molecules vertically up or down, it doesn't matter. So you can see now by this 180 degrees vertical flip, The hydroxy group now is coming toward you. It's still the same molecule. What else is different? The pattern of the carbon chain. So here, look how it goes from down, up, down, up, down. If I flip it 180 degrees to the back, now the carbon chain is inverted. Okay? Down, up, down, up. So one of the things that you need to be very good at is just at flipping molecules vertically and horizontally. Okay? Whenever you flip vertically, as I just did here, the carbon chain that is flat on the screen will be inverted. And anything that is wedged will be dashed in the flip structure and vice versa. Doesn't matter if you flip up or down. Okay? You can also flip this molecule horizontally. So look at this. It's the same molecule. Okay? Now in this molecule that I have here, the hydroxy group is in this carbon, down, from up, down. Look at the carbon chain pattern here. Hydroxy is in the back. 180 degree flip, hydroxyl is coming toward you. Okay? So once again, same. A horizontal flip implies anything that is coming toward you with a wedge bond is going to go down. It's going to go back to a wedge line. Now, of course, because you flip 180, is going back here. It's dashed, but hydroxyl is dashed in carbon, in this carbon here. When I rotate it, the hydroxyl is coming up toward me on this carbon. It's a 180 degrees flip. Okay? So that's a really important skill. And in the last class, we practiced this. Unfortunately, well, I did this program, but I think hopefully this will be pretty helpful for you to see the structure in 3D. So once again, I want to stop here for a second. Any questions that you guys might have regarding this? Is it clear how you flip a molecule horizontally or vertically? And what happens with the carbon chain and with the groups? But if you have questions, just ask. It's clear? That's really important because, you know, this is a lot of practice. Okay, I'll do it once again, no problem. So here is a molecule. So this molecule that I have here right now, the way I have it, look at the picture on the left side. This is a line and angle notation. Okay, so in this line and angle notation, I have CH3 here, CH2 here, CH2 here, CH, this carbon, CH3, this carbon. So the way I have the molecule in 3D on the picture is exactly how I have it in this line and angle notation. The hydroxy group is coming toward me, right exactly right here, okay? Coming toward me, okay? Now, I can flip this molecule and it's still the same. Horizontal, vertical flipping, I can flip it down 180 degrees. Now, when I do that, the hydroxyl is going away from me, but now the carbon chain is opposite. Look at how it's a carbon chain here. Look how it's a carbon chain right here, because I just flip it. So when you flip a molecule vertically, horizontally, you need to look at two things, the pattern of the carbon chain and the wedge and dashes bonds, okay? I can go back again to my initial structure. Here it is, coming toward me, same pattern on the carbon chain. I can flip it the other way around. Same thing, okay? 100, so this flip is once again 180 degrees flipping. You can see beautifully here the 109.5 angle in between the CC bonds of this sp3 hybridized carbon. So that's exactly what we are showing on the other side, right? So you have a carbon with hydrogen coming toward you, a hydroxyl away from you, back on the screen, and a CC bond on the plane of the screen, and another CC bond on the plane of the screen. Okay, so whenever you flip vertically, you have to pay attention to the carbon chain, and you have to pay attention to the substitutions, okay? So this is a vertical flipping. We can also flip horizontally. So here it is, 180 degrees. Now the hydroxyl is back on the second carbon from left to right. 180 degree flipping again. Now it's coming toward you on the second carbon from right to left. That's the flipping. You can flip also from on the other side. It's the same thing, same thing. Second carbon on the left coming away from you. Second carbon on the right coming toward you. Okay, that's yes. So the question is, so you always want to flip the molecule 180 degrees. Obviously, there are many ways. These molecules in solution, they're moving all the time, but we are looking at specific arrangements, okay? So you always want to flip it 180, vertical or horizontally. And whenever you do that, anything that is wedged in one structure will become dash in the opposite, and vice versa. And the carbon chain pattern will change, okay? If it's going up, once you go flipping, it's gonna go down, okay? If the flip is vertical. If the flip is horizontal, anything that is on this side is gonna be now on this side, and then the wedge and the dash will be reversed. All right. Any other questions? Because this is a really important thing to, and we will go back to the drawing later. To review this, okay? So let's go back to the picture, because obviously you won't have the 3D model, right? So the point of this is to be really good at looking at the molecules on paper and being able to flip them and to understand exactly what that is, okay? So here we have, once again, line and angle notation, okay? Has this pattern. Line and angle notation have the same pattern, okay? The hydroxyl is in carbon 2 from left to right. The hydroxyl is in carbon 2 from left to right. So now I can superpose these two because they have the same pattern. I cannot compare pears and apples, okay? I look to have the molecule in the same position so I can compare them. If I try to superpose these two, do they match? No. So clearly, in one structure, the hydroxyl is going toward me. In the second one, the hydroxyl is going away from you. Okay? So they don't match. So are these two compounds the same compound? Or are they different compounds? What do you guys think? So if I superpose them and they don't match, they must be different compounds. They are stereoisomers. So these two compounds, they have the same molecular formula, they have the same connection, but they differ in the orientation in space. This hydroxyl is oriented toward me in this picture. This hydroxyl is oriented away from the screen in this picture. So these are two stereoisomers. Okay? So two different compounds, and we will classify them a little later, what kind of stereoisomers are them. But for now, at least you should know they are two different compounds. Let's look at this compound number C here, compound C, and I want to compare compound C and B. So I could say here A and B are stereoisomers. And then the question would be, which ones? Are they diastereomers? Are they enantiomers? We will go back to that question soon, okay? And then let's see what is the relationship in between B and C, okay? So I look at the structure of B here. okay? Base here, structure of C. So if I want to compare them, the question would be, do they have the same carbon chain pattern in both structures? No. So the first thing that I need to do is put them in the same way, flip it, correct, okay? And you can do a couple of things here. You can, so you can try it to flip horizontally or vertically. Of course, I can see here that the pattern is down, up, up, down. So a pretty simple thing will be to flip the molecule vertically. Okay, so if I flip the carbon chain vertically, this could be the flipping. So I am bringing the carbon chain, remember, toward me, just pulling from the hydroxyl toward me as I did on the screen. And then if I do that, the hydroxyl will be in position number 2 because it's a vertical flipping. If we're doing vertical flipping, the position of the group is the same. And then now, is it going to be the hydroxyl in this position, dash or wedge? After the flip, it's going to be dashed. That's correct, because we just did a 180 degrees flip. Okay, it's going to say here 180 degrees vertical flipping. Okay, and then as a few people said correctly, because we did a flipping here now, the hydroxyl is going to go away from us. It's going to be a dashed bond, OH. Now that we have the two carbons on the same pattern, then we can try and see if they superpose or not. So I'm going to take structure C, flip, I'm going to put it on top of V, and then my question is, do they match? Do they superpose? Yes. So if they match, if they superpose, the question is, are these two the same compound or are they different? They're the same compound. Beautiful. So we can say here that B and C are the same compound, just drawn in different perspectives. Okay, that's a really important thing. So that I want you guys to start looking at. Okay, so now I want to address the next question, which is, okay, so B and C are the same. That's it. A and B are different compounds. We just said that they are stereoisomers because they have the same molecular formula, the same connection in between the atoms, and different orientation in space. Okay? But now we just said that stereoisomers can be classified in two groups. Those that are a mirror image of one another, enantiomers, or those that are not a mirror image of one another, diastereomers. Okay? So, what is the relationship in between these two? Are they enantiomers or diastereomers? So the one thing that I can do, and this is an exercise that I am going to do now, because once you get better, you won't need to do this, but I'll try. I'm going to draw the structure of A here, and I'm going to pretend that I have a mirror here, and then I'm going to draw the mirror image of A. Okay, so the mirror image of A, I'm going to draw it. So if this is going this way, the mirror image will be basically this, right? This, here, here, here. And then the question is, in this mirror image, where should I place the hydroxy group? Should I place it in the second carbon here, from left to right, or from right to left? Which of these? Left to right or right to left? Because left to right, so the mirror image will have here the hydroxy group. That is correct. And the question, next question would be, should I, in the mirror image, should I place the hydroxyl wedge or dash? So a lot of you said dash, and that is incorrect. So it's a wedge bond. If you put a mirror here, you're not doing any flipping. So in the mirror image, the hydroxyl is going to be also coming toward you. Why would it be dash? If it's dash, it's because you flip the molecule. In the mirror image, nothing is being flipped. Okay? The mirror image is just a reflection. And in the reflection, anything that is wedge will still be wedge. Anything that is dash will still be dash, as long as there is no flipping. Okay? So this is the mirror image of this molecule. Correct? So what is the relationship in between these two? If this is a mirror image of one another and they are not superposable, how do we classify them? Enantiomers. Enantiomers, okay? So two compounds with the same molecular formula, same connection between the atoms, different orientation in the space, which are a mirror image of one another, they are enantiomers, okay? And now I want to look into the relationship of the enantiomers. I'm gonna write it here. This is enantiomers. And I want to also look into the relationship of this enantiomer that I drew here and compare this to compound B. Okay? So if I want to compare the enantiomer of A and compound B to see if they are different or the same, first thing first, I need to look one question at a time. So if you look at the carbon pattern in B, the carbon pattern in A, should I do a vertical flipping here, or is that okay to compare? I can just copy and paste for you because no one is answering. So if I put this structure on top, the carbon patterns, the carbon chain, they have the same pattern. So I don't need to do any vertical flipping. Everybody can see that, right? Okay, so if I try to superpose this, obviously they don't match. But what else should I try before making any conclusion? I need to do a flipping, a horizontal flipping. Okay, so if I flip this horizontally, then basically I am pulling the molecule from this side toward you and then reversing the whole thing. So where is the hydroxyl ending up? In the carbon on the left, second carbon on the left, or second carbon on the right, if we do a horizontal flipping. So we're gonna do horizontal flipping, and I'll write it over here, 180 degrees. And as everybody is saying, which is good, so 180 horizontal. Now the hydroxyl will be on the second carbon on the right because I'm pulling the molecule from here toward myself. I'm flipping it 180 degrees. And then the hydroxyl in this position, would it be dash or would it be wedge? So if I'm doing a 180 flip, then anything that is dash is gonna go wedge and vice versa, because in the initial structure, the hydroxyl was a wedge bond coming toward me. Once I flip, I'm gonna send it back. Okay? And now that I flip the structure of the enantiomer, I'm gonna try to superpose these two. And then now the question is, do they match? Are these two superposable? They are. So what is the relationship in between B and A? No. Somebody said, so once again, A and B, we just said that they are stereoisomers because they have same molecular formula, same connectivity, different orientation in space. I'm trying to look now the next question is, are they the mirror image of one another? What do you think? Is B the mirror image of A, yes or no? Yes. Yes, they are. So the mirror image of A is this compound here. Okay? But if you flip it, it's the same molecule just drawn in a different way. So this is the mirror image, but they are just presented in a different way. That's why you need to get good at flipping molecules. So because they are stereoisomers that are a mirror image of one another, we can say that A and B are also enantiomers. Okay? And this is really important because now I want to remember you that because they are enantiomers, they have the same physical and chemical properties. Okay? We will look into that later. So we will practice that more, hopefully in the next class, but now I want to continue giving you more tools to be better at this. If you really can master this, you're gonna do so much better in organic next semester because stereochem is something that we use all the time. Okay, so here is a summary once again. Stereoisomers can be enantiomers or diastereomers. So remember once again, diastereomers, not a mirror image of one another. Enantiomers, they are non-superposable mirror image of one another. So what do they have in common? Is there any other way for you to identify a molecule if it has an enantiomer or a diastereomer? So it looks pretty complex at first. And there is a way to simplify this. So these two molecules can be classified as chiral molecules. And I'm going to introduce a new definition, a new way to classify molecules or objects. Before we were talking about isomers and different types of isomers, okay? Now I'm just focusing on something much more global, okay? So we can classify every single molecule in the world as chiral or achiral. Chirality is such a big concept in science and in chemistry. Objects can also be classified as chiral and achiral. And the definition is something that at this point is familiar for you. Okay? So the definition of a chiral object is an object that is actually cannot be superposed with its mirror image. Okay? Simply, they cannot be superposed with its mirror image. That's a chiral object. And those can be superposed on its mirror image. Of course, if you can superpose, it's the same molecule. So we are not talking about two different molecules. It's the same thing. The reflection is the same as the original molecule. Those are achiral molecules. Okay? Or objects. So here is a pretty easy example. It's just your hands, your left and right hand. If you put your hands in front of one another, and you can do this now, exactly as is in the picture, okay? You can see how the right hand is a reflection of the left hand. Just put it as is on the picture, and you can see how one is a reflection of the other one. If you try to superpose them as you have it on the right picture here, they don't match. The fingers don't match. So basically it means that we're talking about a chiral object. Okay, your hand is chiral. Here is another example of a glass of water. So this glass has no pictures or anything on the surface. If we put a mirror right here, here we have another glass. So can we superpose the right glass on top of the left glass? Do they match if we superpose them? Is there any feature that won't match? They will match perfectly. So a glass of water like this one is not, is an achiral object, okay? Because it is, you can superpose, so basically it's the same thing. Now, if you had a picture on this side, it could be different. So I want to take it now to a different context, and I'll show you a molecule. Okay, here is a molecule. This is a drug that was given to people in the 70s. All right. So let's look at these two drugs. If we try to superpose the right structure on top of the left structure, do you think they match or not? So are they superposable or not? What do you guys think? Try to superpose structure on the right side on top of the left side and see if they superpose. They don't superpose because this dash bond here, so the carbon nitrogen is going on the back of the screen in this structure and it's coming toward you in this one, so they don't match no matter how you, now if you flip it, you can say, well, what if I flip it? So if you flip this, then the CO is going to come toward you and then it won't match over here. So no matter how you flip this, so no matter how you flip this, I'll answer that question now, they don't match, okay? And now somebody's asking me, do they have different physical and chemical properties? So my next question is, what is the relationship in between these two? Are they the mirror image of one another or not? Most people are saying no, and that is not correct. They are the mirror image of one another. Take the structure on the right, flip it horizontally 180 to the left, okay? Now the carbonyl is gonna come here, this bond is gonna go dash, and they will be perfect mirror images of one another. Okay, so they are two compounds, not superposed or mirror image of one another, so they are pair of enantiomers. Because they are the pair of enantiomers, they have exactly the same physical and chemical properties, okay? So, and that's so relevant. So you need so somebody's asking me, well, so I cannot move this in 3D, but basically, once again, take this molecule here, flip it 180 degrees to the left side horizontally, bring the carbonyl to this side. If you bring the carbonyl to this side, this part is gonna go to the back, this is gonna go dash. It's gonna be exactly like this. Or you can do an exercise, draw yourself the mirror image of this and flip it, and you're gonna get this. Okay, I'll give you some more later, so it will be easier for you to see. So the point of this is that these two compounds are two enantiomers, same physical and chemical properties. So in the 70s, when they were giving people this drug, okay, the pharmaceutical industry, they did not know that they had actually two compounds in the mixture, because people didn't know well about enantiomerism at the time. So because when you analyze the mixture, you only get one melting point, solubility is the same, spectral properties are the same, people thought that they only had one compound, but in fact they had a mixture. And then pregnant women taking this drug were having a lot of kids with birth defects, which were freaking people out, and no one knew why was that. And the reason for that was that because these are two different compounds. One compound was doing what was supposed to do, however, the enantiomer was actually doing something else and causing all these side effects. Okay, and we talk about that in the next class, why was that? But the point being is that this actually changed the world of the pharmaceutical industry and chemistry, because from that point on, every single drug that is given to people, if the molecule is chiral, once again, this molecule is chiral because it's not superposable with its mirror image. If the molecule is chiral, it can exist as enantiomers. So any chiral molecule will have an enantiomer. Okay? So if any company comes up with a drug and this drug is chiral, first thing they have to prove now is that the enantiomer is not a picture. Okay? Unless they prove, which some companies do, that the enantiomer does not have any side effects. I encourage you to look into ibuprofen online, read about the structure of ibuprofen, and I will relate the topic to that. It's very interesting because ibuprofen is chiral, and it's giving us a mix of enantiomers to people because there is no side effects of the other enantiomer. So basically, somebody was asking me about so basically that's the relevance of stereochemistry. So now it's so important to determine relationship between molecules, to see these molecules in 3D. Okay, just to give you an idea. So here is another example of another drug which is chiral, and I'll talk about that for the next class. So no, so somebody's asking me, so diastereomers are chiral. So we will get into that. Diastereomers could be chiral or achiral. Enantiomers are always chirals. I'll show you now why. It's gonna get a lot easier now. How relevant this is: 66% of all drugs are chiral, and 51% are being studied as a single enantiomer. So any chiral molecule can potentially exist as a mix of enantiomers, and that is very important in chemistry and in biology. Okay, so next thing that I want to question that comes to your mind should be, okay, so we're talking about chiral molecules, enantiomers, diastereomers, and then how do I identify a chiral molecule? I just said, because obviously drawing the mirror image, superposing the mirror image can be very challenging. It takes time to get used to that. But then the question is now, is there any features that you can find in a molecule that will make the molecule chiral? Is there anything in the molecule that you can look for, and if you find it, then you can say this molecule is chiral? You don't even need to draw the mirror image or anything like that. You can make sure that it's chiral. Or the reverse. How can we identify an achiral molecule? A molecule that is superposable with its mirror image. What feature could we find in a molecule that will make that molecule achiral? And that is a really, really, really critical thing to know in organic chemistry and in chemistry in general. And it's a pretty simple thing. And it's something called, which a lot of you might know at this point, elements of symmetry. Okay? So, and we will get into what is that exactly, but any chiral molecules will never have any element of symmetry. Period. And pretty much there are some exceptions to this, but for now we can assume as a general rule. The exceptions we will talk next semester. Achiral molecules will always have at least one element of symmetry. So now we need to start looking at the molecules in 3D in a different way. Okay, so now you look at a molecule and then you ask yourself, is there an element of symmetry? Yes or no? If there isn't, the molecule is chiral. If there is, the molecule will be achiral. And when I'm talking about element of symmetry, I'm talking about basically two things. One is a plane of symmetry, And we define a plane of symmetry as a plane passing through an object and dividing this object in two sides. Okay, so we need to imagine a plane, 3D plane passing through an object, dividing the plane in two sides. So one half is the mirror image of the other half. Let me show you here. Look at the molecule on top here. Okay. So this carbon here is sp hybridized. The angle here is 109.5. Okay, this is a different way of drawing the molecules. In this case, you see two wedge and two dash bonds because it's basically showing you two coming toward you and two away from you. So the plane is now perpendicular to what we just saw before. But in any case, a plane of symmetry will be right here. So if we draw a plane across this carbon, plane that is passing through this chlorine atom, this carbon, and this hydrogen, by the way, a plane is defined by 3 points. Okay? 3D plane is always defined at 3 points. So a plane of symmetry is a point here, point here, point here. These 3 points makes a plane here. When I draw a plane in 3D, I see on the left side a methyl group coming toward me. I see on the right side the same methyl group also coming toward me. Obviously, this left side is the reflection of the right side and vice versa. So this is a plane dividing the molecules in two sides, one being the reflection of the second side. This is the definition of a plane of symmetry. Because this molecule do have a plane of symmetry, we can say that this molecule is achiral. Look at the 3D picture here. Okay, it's much better. You have the carbon right here, methyl group here, methyl group here, chlorine atom here, hydrogen here. Once again, a plane is defined by 3 points. 1, 2, 3. Hybridization of the carbon is sp3. The plane is right across here. This plane is dividing the molecule in two sides, a right side and a left side, and they are the mirror image of one another. Same groups, and one is the reflection. So a plane that divides the molecules in two sides that are the reflection of one another, that is a plane of symmetry. Therefore, any molecules having a plane of symmetry will be classified as achiral. If the molecule is achiral, it means that it is superposable with its mirror image. Therefore, it's the same thing as reflection. Okay, so that's why it's achiral. So I want to show you now here the molecule on the bottom. Same thing. Now I have carbon here. M is methyl, Et is ethyl, ethyl is CH2, CH3, chlorine, and hydrogen. If we draw a plane over here, once again, a plane divided by 3 points, 1 point here, 1 point here, 1 point here, a plane right here, dividing the molecule in two sides, one side, second side. Now what happens is that the group on the right side is not the same as the group on the left side, so therefore, this side is not a reflection of the other side. So the plane is not dividing the molecule in two sides that are the reflection of one another. You can draw a plane across here too. Plane containing this group, this carbon, and this group. If you divide this plane, same thing. On one side you have away from you chlorine atom, away from you here a hydrogen atom. Even though the orientation is a reflection, the groups are not the same, so this is not a plane of symmetry. Because this molecule don't have any element of symmetry, we can tell that this molecule is a chiral molecule. Okay, so that's the definition of chirality. Okay, and the second element of symmetry is a point of symmetry. So here is some other examples of plane of symmetry, by the way, before I move, so you can have in in geometry, this is a plane of symmetry, okay? Plane here dividing two sides, one is the reflection of the other. It's another example similar to the one that I said before, okay? A molecule with a plane across here, sp3 hybridized carbon once again, plane of symmetry, a chiral molecule. So the second element of symmetry is a point of symmetry. Point of symmetry is a point from which you will find the same groups on opposite sides at the same distance. So this point here, which is in the center of the square, up, down, same groups, opposite sides, same difference. That's a point of symmetry. Opposite, same group, same distance. It's more challenging to find point of symmetries as compared to plane of symmetry, and that again requires practice. Okay. But the idea here is, once again, now we can classify molecules into chirals and achirals. And the one thing for now that will help you to which molecules are chirals and which one are achiral will be element of symmetry. And we will practice this more. So any molecule containing an element of symmetry, a plane or a point of symmetry, will be achiral. Any molecule not having an element of symmetry will be chiral. If it's chiral, it can have an enantiomer because it's not superposable with its mirror image. If it's achiral, it won't have an enantiomer because the mirror image is the same molecule.